Hello, let us start on lecture 11. I think I counted right. So remember that we are here, and there is a midterm next week, and then after that it's just the final. Please make sure you're looking at this page with all that information that we've talked about before, and there's a fun little video review down at the bottom. And remember that like I said last time, everything from heaps onward will not be on the midterm. All of the topics on the study guide, though, are fair game. Okay, so with that, I think I can safely get out of Safari. And, oops, let us talk about some more dynamic memory allocation. So before I start this lecture, these slides at least, that are essentially all about linked lists, let's talk about the heap some more. So the heap, your book calls it this thing called the free store. But no self-respecting computer scientist says free store, so it is the heap. That's all I will ever call it. The heap is a place where you can allocate memory from, where you can perform these things, these dynamic memory allocations. All right, this memory lives until you free it. That is, use the delete operator on a pointer into the heap. Okay, so when you make stuff on the heap, they come in pairs. You say new, and there's always supposed to be, if you don't want any leaks, remember, there should always be a corresponding delete. So new makes the thing on the heap, and the delete gets rid of it on the heap. So if I am making a variable on the stack that points to the heap, this is what it looks like in terms of memory. So let's pretend we're in like the main function, and we say something like, I don't know, int star p equals new int. So what's going to happen is on the stack we have this new variable called p that holds an address of an integer. And it is going to point to, it's going to hold the address of a brand new shiny location on this part of our program's memory called the heap that we've just allocated space for one integer. And so now p is pointing to that box on the heap, and we can use it to set stuff. We can say like star p equals 5, things like that. And now it has an actual value. And then finally, once we're done using this int pointer to this place on the heap, once we're done with this location, like we've used it, we've printed it out maybe, we'll always then go and call delete on the pointer itself. All right, and that'll go and get rid of this thing in the heap. And then you should never, you should either reassign p or never dereference it after it's been deleted. That is, weird things happen. You shouldn't dereference a pointer into the heap after the memory associated with that address has been deleted. Okay, so just try and remember that. And I think what I want to do now is just make a quick review example of heap stuff. And while I do that, let me quickly start a little timer for myself. Okay, let us go to code. So here's my heap.cpp from last time. I'm going to essentially copy that and make a heaps2, should have been heap2.cpp for today's lecture. All right, so let's get rid of this function. We don't need it. And let's kind of talk about the idea that we are, that I kind of drew up there. So let's say int star p equals new int. So now I have a brand new integer on the heap. And p is the way I can access it. So I can say star p equals 42. And the beauty about this is this P, or the address that P holds, is a place on the heap that lives forever, for as long as we ask it to. So if we made this variable inside of one function, it won't go away once that function returns because it's made in a different place. So we can now pass along that int to, I don't know, let's make a foo function that takes int star I, let's say, and let's use that to, I don't know, increment the thing that it's pointing to, so we can do something like foo of p. This will give the heap variable to the foo function. And then maybe foo even can pass around this I to some function called bar. I could still call it int x, int y, I, int j, whatever. And we'll say j plus equals 1 after we call bar on I. So foo, not only, we're not only giving this p to foo, and indirectly we give p to bar as well. So this place on the heap that we made for ourselves, we're just passing around everywhere. And that's the beauty of it. So if I see out star p now, it has taken a trek, and it's been some places, and it should now be 43, 44, right? So that's what we should see. And now that we're done with p, it's gone on its vacation. It's ready to be deleted. Delete p, and then it goes away. So this is kind of just a fancier example of making something on the heap, using it in a bunch of places, and then once you're done with it, removing it. And actually, one more thing just to drive the point home, let's continue with that, create an int function from last time. So instead of making our new int here, because main does live forever, it's on the bottom of the stack, let's have instead a create an int on the heap function, which will return an int star. Create, will it try and do it for me? An int, no. I'm just going to copy and paste it then. Whee. Return new int. All right, so that just drives the point forward as to this memory is not on the stack anymore, because otherwise it would have gotten deleted once this function returned. Okay, so let me compile and run this just to prove that it's doing what we think it's doing. So it should print out, in theory, 44. There we go, and it's doing the right thing. So just briefly, let's talk about the stack and the heap for this one program, and I think that should be enough to get stacks and heaps comfortably in your minds for now, before we do fancy things with them. All right, my computer is going very slowly for some reason. We'll figure that out later. So I need to scroll way down. So remember that the stack is there. So I'm going to put it right there. And so the first thing that we do when we run our program is somebody's calling main for us. Usually the terminal's doing it. So from main, we make an int called p, an int pointer called p, that we then use to populate with this create int on a heap thing. All right. So first, well, main's making this p, and we're about to fill it with whatever we get back from create int. Okay, so that's happening. And what create int is doing, it doesn't have any local variables. It's just going to return a brand new integer from the heap. All right, so on the heap, create int, this function is going to make for us a brand new place, brand new box that holds just one integer, and will return back the address of that thing. Okay. So essentially, let's pretend this was address 100. This is about to return address 100. So p holds 100. That's the address of this place on the heap, and now we have a way to talk about it. Okay? And then create int returns. So it had no local variables, and that was important because now we're still able to access this box. It was in a separate place in memory. All right, so now we got our p. It's populated, it's filled, because create an int returned to us. Now we'll set it to 42, the place that p points to. Oops, that's kind of ugly. There we go. And then we will call foo with p. All right, so what does foo have? It has a local variable, or a parameter, called I, and that will get made when we call the function. So this is foo. It has a variable called I, which is itself a pointer, and we gave it p as that value, so it'll get copied into there, and now I is also pointing to this place on the heap. Okay? And we'll use I then, we'll go through I, not p, to increment this place on the heap, so now it's 43. And then we'll call bar. So foo hasn't returned yet. It's still waiting on bar now, which has a parameter called j, which functions like a local variable because it has it gets space made for it in the stack frame for bar itself. And again, we're passing along the value of I into j. And now we got 3 places to talk about the same thing. All right, now through j, we're going to increment 44. And now look what happens. Bar returns. Boop. Foo. Done calling bar. Foo returns. Boop. Now we're back in main. And we print p out. We print our 44, and then now we're done with p. So we delete that. Now, let me use a different color for that one. Whee. All right, so that is essentially the stages of that program being run. And that's the beauty of using the heap, because I can make this variable outside of everything. Like I could make it in its own little function. And that variable, this int, it lives for as long as I ask it to. That's the point of the heap. That's what it's very good for. And I can keep on deleting and remaking things on the heap so I can reuse that information. And that's quite different from a global variable, which has to live for the life of the program. I can't ever get rid of it. Okay? So heap's good for things that constantly need replacing. Or you just don't know when you run the program if you'll need it yet. And that brings us now to this fancy thing called a linked list. So with the time left we have today, I will talk about linked lists. So a linked list is what's known as a data structure. It's a way of organizing data. And we already know about one data structure already. We know arrays. Those are our favorite data structure so far. Those put things together in like a contiguous way. Okay? So that's the idea. So since you are already like experts with arrays, linked lists are a data structure. They are just another way of arranging data, arranging information, let's say. So you already know about the array data structure. So let's talk about the pros and cons of arrays. I'll just type that some more over here. So pros and cons of arrays. So let's have some pros, and then over here let's have some cons. All right. So I would like you to think about this yourself before I get into it. But assuming that you've done that so far, one thing that arrays are really nice for is that they're contiguous in memory. Contiguous in memory. You immediately know where every index is. You know its address, because if I had an array in memory, like here's my array ARR, it starts at like, I don't know, address 100. You know the next thing is in 104. You know the next thing is in 108, and that's super nice because it's very easy to add to an address and immediately tell your CPU to go to this place in memory. Okay? So it's very fast. Arrays are nice because you can immediately get to a place. It's super fast to do that, to access memory. Relatively, that is. So it's easy to get to a location, any index into that array. One con or I would say the main con of an array, is that it's hard to add stuff in like the beginning. Assuming you start adding things to an array in like left to right order, it's hard to add stuff in to the beginning or the middle. And I'll give you an example of what that means. If you run out of space, you're out of luck. So let's talk about those two cons. Let's pretend, here's my array again. It's holding 1, 2, 3. Let's say, let's say it's holding 1, 2. And I want to add a 0 right there. And actually, just to drive the point home, let's say it's holding 1, 2, 3. It's a size 4 array. But I want to add a 0 into the front because I want it to stay sorted. Well, immediately, I'm kind of out of luck if I want to save everything. And I have to move all these things over. The 3 has to go here, the 2 has to go in its place, the 1 has to go in its place, and then I can finally put the 0 up in here. Because now I have a 1, then I have a 2, then I have a 3. So that took a lot of effort. I had to shift everything over. Do you see that? That's no fun. And now, assume I wanted to add a 4 here. Question mark. You can't do this. You allocated space for an array of size 4. You can't just start writing past the end of it. That's undefined behavior. You don't have access to that memory. You will eventually get a seg fault, or something horrible will happen. So those are some pros and cons for arrays. And so enter linked lists. They're a different way of organizing data, and they have some different kinds of pros and cons. There's always a trade-off. And there's also a bunch of different kinds of data structures that we just don't have time to learn about in this class. But if you take CS24, for example, you'll learn about plenty of them. And a lot of them in this picture, I don't know where this picture was found, but a lot of them are kind of incorrect. Like, I wouldn't call this a list. I'd call it like some type of tree, maybe a B tree. And then, don't know what kind of, I guess this could be this could maybe be a stack, but it's got a stack pointing to trees, and I don't understand it, but this is what a linked list looks like, at least. So what are linked lists? Well, they involve the heap, so it's a good thing we learned about that. A linked list is just another way to represent a bunch of data of the same type. So let's say I had an array, also known as an array list, with 1, 2, and 3 in it. That's an array. I could make the same thing. I could make a list 1, 2, 3 in this way. So on the stack, I hold a pointer to the first thing in that list, so the 1. And the 1 lives kind of alone. It's separate from the other elements of the list, and it's called a node. So this is the 1 node, we'll say. All right? And then the 1 node holds its own data, and then it points, using pointers, to the next node of the list. There's the 2 node now. And then finally, the 2 node holds its own data and points to the 3 node in the list, which happens to be the last element. And the last element of the list, its next pointer, is this special null address, because that one doesn't exist, and we know we're at the end if we check for that. Okay, so that is, in a nutshell, what a list looks like. And you don't have to think of like how many things you need ahead of time. Okay, so this is what a list looks like in memory. So parts of it on the stack, and usually all the nodes live on the heap. Okay, let's talk about that. So a linked list is made up of individual things called nodes, and each node holds 1, a data value for the current element of that list, and 2, a pointer to the next node in the list. Okay, so it's kind of like sharing the work. So here is like my list L. It's a pointer to L lives on the stack. That's a pointer into the first node living on the heap, which I'll draw like this. 1 arrow, 2 arrow, 3, and the last element's next pointer is 0 or null, and I'll draw that with a little slash. So for example, this is the one node, and the one node's next value holds the pointer to the two nodes. This is like the data part of the node, and this is like the next part of the node. Okay? So just like an array is a pointer to its first element, a list is, an array is represented as a pointer to its first element. A list is also, well, a list is represented by a pointer to its first node. And so the idea, the pros and cons of linked lists now are a little bit different. Pros of linked lists, and over here let's do cons of linked lists. So the pros of a linked list kind of offset the cons of an array. It's really easy to add stuff to the front, also the middle, if you have a pointer there immediately. And I'll talk about that in a second. What was the other con? If you run out of indices, you're out of luck. You can keep adding nodes by allocating more memory on the heap. So you need another node? Just say new node. No worries. And so if I want to add the 0 node now, look all the things I need to change. I need to make a brand new node on the heap. Hold 0. I need to reset this next pointer, or this list pointer, to be this new start of the list. And then now I just need to reset this next pointer to point to the old first node, and now it's the second node. See? Beautiful. Quite easy. One of the cons, though, is now it's hard to get places. You have to follow pointers to get, you have to follow a lot of pointers to get anywhere. Because it's not the case anymore, like this address is 100, this address is 108, this address is 116. No, when you make things on the heap, they're just given a random address, just that next free space in memory, which is not necessarily contiguous. So if I want to get to this 2 node, I must go through L. I must go through L, and I must go through this first node, I must go through this node. I need to go through all of those pointers. I need to follow this pointer, and that pointer, and that pointer, and then finally I'm at this node that I wanted to get to. So that's really unfortunate. You have to follow a lot of pointers to get anywhere. But that is your trade-off for being able to add stuff so easily. Okay? So pros and cons of linked lists. And maybe you don't worry about that if you're always only touching like the first couple nodes. Not an issue. You can also save the pointer to the last node, and we'll talk about that in just a second. So this is a new type of data structure. It's called a linked list, and I hope it's getting a bit less vague in your mind. I know we just talked about it. So now let's make it even more concrete. Let's make a list now with 2 nodes in it. Let's make the list 1020. So I want to make the list 1020. I'll use Python notation. And so if I want to do this, let's say in C++, using things, I'll make structs for my nodes, and I'll end up with memory that looks like this eventually. So I'm going to make this struct node, which holds my int data and then a pointer to my next node. And this is what it's going to look like in memory. So let's also make a L that points to the first node in the list. And then on the heap, I'll make a 10 node, have it point to the next node, which is the 20 node. And then that node will be the last one, so I'll have it return, or have its next pointer be null. And that was too many lines up in here. Let me fix that. There we go. All right, so that's the idea. This is what we want to make now in code. So let's go to some code and get started. All right, so let me make a file called linkedlists1.cpp. And I can mostly include a lot of this stuff, so let's just get ourselves started with all this boilerplate. All right, so we need to make a struct node now. This will represent a single node in our linked list. Okay, and so it holds two things, remember. The data value that that node holds, and then also a way to get to the next node, which is a pointer. So int data, and the next pointer, well, it's a pointer, sure. It's a pointer to what? It's a pointer to another node. What? This should make you a bit uncomfortable. This is weird. We're using nodes to define nodes. So like we're using nodes inside of nodes. But really it's node pointers. So it doesn't get super weird and infinite. But this is a bit odd. This is called a recursive data structure. And if you've learned about recursion, we'll touch on it some more at the end of this class, but this is a recursive type, we call it. So we got nodes inside of nodes, and that makes sense because this next place is another node. It's logical. All right, but it is a bit odd, and I wanted to talk about that, just highlight it. Don't let that confuse you. All right, so now let's make our first element of our list. So in this class, we'll say that here's some terminology. We'll call the first node in the list the head. And this is common terminology. This you'll hear for the rest of your life if you ever talk about linked lists. The second piece of terminology is just for this class. And maybe 24 and 32, I don't know what the professors are doing, but I don't agree with this notation, but we're going to use it. We'll also call the last node the tail. The reason I don't agree with this is because if you ever get into something called functional programming, the tail of a list is every node except for the head. But in this class, we'll call the tail the last element, the very last node only. All right, so head and tail. So in this case, this is the head, this is the tail. It's only got two nodes. All right, so that's that. Let's go back to our implementation. Let's now remember what we're doing. We're trying to make this list with the first node being 10, the next node holding 20. So let's make two nodes. So node star 10 and node star 20. And remember, these get made on the heap. So this is a new node. This is a new node. So 10, it's data. And remember, this is a pointer to a node, so I can't use the dot operator immediately. I'll either have to dereference it and do something like that, equals 10, or alternatively, in the fancier way, the way that you'll eventually get used to if you aren't already, you say 10 arrow data equals 10. That's exactly equivalent to this fancy parenthesization and dot operator. It kind of does them both at the same time. Then 10's next is the address of the 20 node. Okay? And then 20, its data holds the number 20, and 20's next is the null pointer. All right? So that now, in memory, we've essentially just made this list. And we have some extra stack variables like 10 and 20 that are pointing like that and like that. But let's now make our last final pointer called, let's make it be called head, because that'll be a common thing that we do in our your future lab that involves a linked list. So we'll say the head of the list is the first node, remember, so it is the address of the 10 node. So now we have made our list in memory. Beautiful, huh? All right, we did it. And so what we've done is we added those two nodes immediately. I did skip the empty list bit because I want to talk first about what it means to be an empty list. And somehow I got rid of that null pointer. So the end of the list is always the null pointer. It also is helpful and useful to regard an empty list as just a pointer to null. So we also use the null pointer to represent the empty list. So the list without any nodes in it. And that would be represented with like a L pointer nowhere. Like it's holding null, it's got nothing in it, it's pointing nowhere. So that will be our empty list. So an empty list is just represented by the null pointer, okay? So if you wanted to start with an empty list, you'd say something like node star head equals null pointer. Head points to the empty list because the empty list is just nothing in it, null. And then we make our two nodes, and then we'll set head to be the first node, and now head points to a non-empty list, to the list 1020 now. Okay? So I hope that makes sense. So that's what we're doing. And now we have a list with 10 and 20 in it, starting from an empty list. All right, so now things get fun. All right, here's 4 questions in one. So take some time to think about this, and then we'll come back. So here, pretend I had a pointer called head that points to the first node, holding 1, which points to 2, which points to 3. All right, go through all these in your brain and figure out what these things are going to point to, what they're going to evaluate to. All right? All right, so head data, what's that going to do? So remember that arrow translates to this. Oops. Dot data is equivalent to star head. Oops, sorry. Got ahead of myself even. It's not head dot data, it's head arrow data. It's equivalent to star head dot data. So it's dereference head, so follow the pointer. Now we're at the node, and then get the data there. So that's 1. Okay? So this one is going to be A, and I can't really circle anything now, can I? So let me try and draw. The answer here is A. Oh, A? That's an A. Good enough. All right. So, all right, head next data. What do you think that's going to be? Head arrow next arrow data. And remember, we do this all again. Head arrow next arrow data. Well, this is equivalent to, this is going to get hairy now, dereference head, use the dot operator to get to the next variable inside of it. And then that itself, we're going to use the arrow operator on. If you draw your parentheses, it'll look like that. And so now we got to dereference that now, and then call the dot operator on that with data. Okay, what does that even mean? So follow head. We're at the 1 node now. Let me use this. So now we're here. All right, get the next. Follow that arrow. So now I'm here. Get the data. So now I'm getting the 2. Okay, I hope that makes sense. So this is a B. All right, so all right, what's head next data going to be now? I think if you follow along, first we go through head. Now we're here, get its next. Now we're here, get its next. Now we're here, get its data. Now we're here. Okay, so that's C. C, please. No. That is a C. Okay. And, all right. The final one, and then I'll show you the trick. Actually, let me show you the trick now. So this was hard to follow, right? If you go and convert this, I mean, it eventually works, but here's an easier way to think of that. A trick to following along with diagrams. Every arrow operator in code followed an arrow in the diagram. Now, isn't that cool? So let's confirm that. Head arrow data. We followed 1 pointer. We followed this 1 arrow. Now we're here, and we can get its data. Head next data. Followed 1 pointer to get its head. Then we followed the next pointer, this one, and now we're here. You see that? That's super helpful. and I'm not allowed to delete that for some reason. There we go. Isn't that nice? So then head next data is going to follow 1, 2, 3 arrows, and so if you didn't have an arrow, you'll end up somewhere here at this last node, and you can get its data. All right, so number 4 is the fun one. So head, next, I'm here. Next, I'm here. Next is the null pointer. Arrow data, there's no more arrows to follow. Oh man, it's not null anymore. I get a runtime error. So this is E, we're dereferencing null. So this is going to be interesting there. So that last one, when you go this far, head, arrow, next, arrow, next, arrow, next. At this point, we are hitting null. That is, we just got here. All right, and then arrow data is, remember, first dereferencing, then using the dot. We just dereferenced null. And I hope you can follow that. And please try that out yourself. Try it in code and just watch it fail. That's fun. Or not, depending on how you think about it. So that is that. And yeah, lots of traversals happening here. All right, so now let's make fun functions that work on linked lists. So the idea is let us make it a bit easier on ourselves. Let's make a second data structure called linked list now. So we already have nodes. Node, the node struct holds individual nodes. Let's make a linked list struct to package up an entire list. Okay, so I don't have to like just have a bunch of L pointers everywhere. Let's have things called like head and tail. So let's do that. So let's have struct node and struct linked list now. A linked list will package up all the nodes. It'll hold the head and the tail pointers, right? So struct linked list holds 2 pointers to nodes, head and then tail. So head is the first element of the list, and tail is the last element of the list. All right, so instead of doing all this stuff, let's put this list inside a linked list object, and then we can just pass that around. Linked list struct, something of the linked list type. So let's make a linked list on the heap. Why not? Let's call it L, new linked list, and we can say L. Well, it's got to have a head and a tail. And what's the head? It's the first node in our list, and so it's going to be 10 because we made the list 10, 20. 10 is the first node. So the address of the 10 node, and then the tail is going to be the address of the 20 node. And now we've just packaged up our list into 10 to 20, into head and tail, and now we can just pass along this linked list. And the tail node is really nice because it allows you to immediately get to the end of the list and like add stuff to it. It is nice when you want to add stuff to the end, because then you can just look at the tail. Whereas the head is really nice if you want to add stuff to the beginning. It's kind of like the dual. All right, so let's now make this function, insert to head of list. And so let me copy most of this, and let's make a linked lists 2 file, where we can use that function to make a list 1, 2, 3, let's say. Let's use the insert to head of list function to make the list 1, 2, 3. So this doesn't affect the tail really, except for the first time. So let's start from the empty list, all right? So let's redefine our definition of empty now. We'll say instead of the null pointer, let's say we'll use the null pointers to represent the empty list, because now if we use our linked list, like here is our linked list L, it points to on the stack a linked list object, struct, or sorry, this is stack. On the stack, we have L, and then on the heap, we have first a linked list object, which holds the head and the tail, we'll say. And so now I'm using that different kind of struct diagram that I've just kind of been glancing over, just getting used to it up until now. So this was a linked list, right? This was our linked list that had a head and a tail. And all of our nodes, let's do 10 and 20. So in our previous linked list 1.cbp, if we use the linked list data structure, it's doing this. And remember that these nodes even, you could technically draw them like this, like we've been drawing our structs. Because we've got a data, we've got a next, and this guy's also got a data and a next, and that was not enough room. So it had 10, and then it pointed there, and then it had 20, and then it pointed nowhere. And these all need to be a lot longer. So you can draw things like this. So this is us using our linked list variable, something of the linked list type. I'll say linked list object, pointing to a node object, pointing to another node object. That was our list like that. Equivalently, and it's a lot easier and faster to draw it like this. Or equivalently, we had our L that pointed to a linked list that had a head and a tail that pointed to two nodes, 10 and 20. Which one would you like to draw? All right, so that's the idea. So let's now use our insert to head of list function to make the list 1, 2, 3, and we'll start our list being empty. So the empty linked list, if it wasn't clear yet, will have null head and tail pointers. So if head and tail pointers. So if head's null and tail's null, your list is empty. So let's start out this list empty. All right, and then we'll use our insert to head of list function to make the list 1, 2, 3. So what's the order in which I should call insert to head of list? Is the new question. So let's first copy this. This is the function we're about to make. And I like my stars over here. So this function, what it's going to do is it's going to adds one node to the start of the list. That's represented by this h variable here. All right. So should I be calling insert to head of list like this? L1, 2, 3. Should I be doing this? Well, let's think about this. It's going to insert to the head of the empty list. It's going to put 1 at the start. All right. So now we have 1. After we call this, we're going to pass along our list, which now has 1 in it. We're going to add 2 to the start of it. And then finally, we're going to add 3 to the start of that. So this will give us the list 3, 2, 1. So what I should have been doing is adding them backwards. Okay? All right, you see that? This will then start with 3, add a 2 to that 3, and then it'll add a 1 to that 2 and 3. All right, so we do it backwards. And then now we'll have that list, and well, shoot, is there a way to, I'd really like to print it out eventually. We'll make that function at the end today, I guess. All right, let's, we want to test that this is correct. So eventually we're going to write some print functions. But let's just get this working for now. So insert to head of list, what's it going to do? Well, we're making a brand new node. Make a new node and put it at the head of the current list. All right, so let's go through it. Let's say we're about to add this 3 node. Let's make our new node. So node star new node equals new node. What's its value going to be? Well, it's always going to be holding whatever we pass along. So new node's data is going to be the value that we want it to be. So now I have the node. Now place new node at the head of H. All right. So in essence, we need to do this. H's head must now become new node. Okay? But the order really matters now. You can't do it right here. You can't do it right now because we just lost the old head. You see that? We had no other way of getting to that. So let's remember, or let's do things a bit differently. Let's set the next first. What should be the next node that comes after this node? So for example, if I'm about to add 2, it should be pointing to, as the next node, the one that already existed, the old head. Because, let's say, I had the list with 3. That's my list. And now I just made the 2 node. This was the old head. We want 2 to point in its next pointer to the old head because we're going in front of it. All right, so we're going to do that. New node next becomes whatever the old head was. All right, and then we can successfully change the head here. Now, one last thing. It's possible that we're inserting into the empty list. And let's pretend that we were doing that. So let's pretend we had a list. Here's our H. It's pointing to a linked list that was completely empty. And our code so far, let's say we were adding 3, our value was 3. Well, so far we would have made our new node that held 3. We could set 3's next to be the old head, which is correct. We're going to make a 1-element list. Its next pointer should have been null anyway. And then we'll reset the old head. We'll reset the head of H to be this new node that we made for ourselves. The one thing that needs to happen now, that doesn't happen any other time, is we also have to change the tail. So in the empty list case, we also have to change the tail. That's the only time that we have to do this. Because otherwise, if we had, well, let me just go through with this. The first and the last node now is the 3 node, okay? And now if I wanted to add the 2, notice that only the head needs to change. You see that? I hope that makes sense. The tail is always the last node, and we're always inserting to the front, so if we already have something there, we didn't need to ever change the tail. But only in the first case, though, if we had an empty list, we better work on changing that tail. Okay. H's. So we'll just check for that. If H's tail is equal to the null pointer, and some people are fancy, like, because remember H tail, if it's null, it's set to 0. Some people check for that with like integer comparison. We'll say not H tail, because this will make 0, and then not that will make 1, which is kind of confusing, but you'll see that. So I'll just check for null. If it's null, then the tail is the head as well. Or you could say H is make it the head because that's what it should be, or we could also say new node because they're the same at this point, because we just set the head to that. Okay, so that should be a correct function, and now if I were to run this, we're going to end up with the list in L holding 1, 2, and 3. But right now, sure, we have that list, we can't do anything with it. We don't have a print function, we can't see out a list, you can't index into L, it can't be like L of I. We gotta do fancier things. We gotta loop through the list now. All right, so we need to figure out how to iterate through this list. let us, in order to learn how to do that, let's make a length of list function. Because in theory, it'll give us some confidence that this function was right if the length of list, L, if that were to output 3, we would be pretty confident that we're doing the right thing for this function. Yeah? So let's try and make that function. The idea is, it's going to return an int. It's going to take a linked list. And it lives on the heap, so it's always a pointer to a linked list. We're eventually going to return a count, so let's start our count at 0, and then we'll return our count. And now we need to iterate through the list, increasing count with each node we see. So how are we going to do that? Oops, I went to the wrong desktop. So if we had a list, let me now draw our list. L points to a linked list object, which has a head and a tail, which holds 1, then 2, then 3, which then holds null. So the idea is we want to iterate through this list. Let's do this. Let's make a pointer called, I don't know, n. That's the current node we're looking at. Let's start at the head. And then every time we iterate, we'll keep on advancing n to be whatever its next pointer held. And then eventually, once we say n's next here, n will point off to null, and then we'll stop our looping. So that's the idea. So idea for looping through a list, print out the or start at the head, and keep a pointer that starts at the head and advances to its next node, or to the next node, each iteration. So that is the idea there. And let's go with that. Let us do for, or actually let's start with the while loop. Let's say node n. Let's start it at L's head. And our stopping condition for n is while there's still a node. Let's continue. We just saw a node, so count plus plus, and then we can say n equals n next. So that's the idea. So how do we know when to stop? Well, n starts out being the head, then we advance it to be the next node, and eventually n's going to become null. We don't want to continue there. So we know we're at a list once n becomes null. All right, so that should be our stopping condition. Keep going while the pointer is non-null. And so that should work. So let's print out our length of list now. Let's say make linked lists 2. Lists 2. Oh, oops. All right, let's continue. Linked list 2. It's 3. Awesome, awesome, awesome. So this is kind of working. Another thing that we'd like to do is to be able to just print out the list. Let's make a print list function. Let me confirm that, oops, I'm always going to the wrong one. Let's confirm that, yeah, the last one is a fancier kind of operation. So let's make a print list function. And so let's output for the list 1, 2, 3, the string 1 arrow 2 arrow 3 arrow x. Let's do that. Okay, so void print list linked list L. That should be a lowercase I. Again, well, string. Let's create the string that we're going to output. Let's start out with emptiness. And let's start iterating. So instead of a while loop, I'm going to use a for loop. And just to get you used to this kind of thing. So, all right, so for node n equals the head of the list, that's my initialization. And I want to keep on looping while my node isn't null. And to advance the pointer, to increment it, in essence, we're going to say n equals n arrow next. So this is a perfect example of a non-numerical for loop. This will take a while to wrap your head around this, but it's really nice. So, all right. So now all we have to do is, or actually, we don't even have to make a string. We'll just use cout every time. So let's output our current node's data, because that's the idea. We'll start off at this node, print out the 1, print an arrow, print the 2 after we advance, print out the 3, print an arrow. All right, so output the data, then print an arrow. Okay, that's the idea. So cout and data, cout an arrow. And I encourage you to walk through this code and make sure it's making sense in your mind. So this will print out 1, arrow, 2, arrow, 3, arrow. Once it's done, then it'll stop. And now all I have to do is print out the x. And I guess a new line would help too. All right, so let's watch that work. Let me actually go up to the code while I run it so that you can see it working. We're passing along the list 1, 2, 3 to this function. We're using a for loop this time. Isn't that cool? All right, so now the idea is we're done with the list. We're finished. Let us delete the whole thing, free all of its memory. So we'll say free linked list. No. Well, we're going to implement it, yes. So that'll be nice. Let's do that there. I don't see a reason why it needs to return an int, so let's make it a void. We'll call it now. Free linked list L. And the idea is we now have to somehow loop through all these nodes in our list. Delete, delete, delete. And then also we need to remember to delete our original. There we go. The linked list itself, because all this stuff, oops, go back please. All this stuff is on the heap, remember. So we need to delete all of them. We have one linked list. Whoa, sorry, my computer's hating me right now. We have one linked list object and 3 nodes. Yeah? So we need to delete all of those. And the idea is, when we're deleting things, the order really matters. Because if we delete this linked list first, realize that we just lost access to all of the nodes, because we cannot follow an address that we deleted, okay? We can't delete the linked list part first. And I'll call, instead of part, I'll say object. Get used to that term. So we can't delete the linked list object first, because then we lose access to the nodes. And technically you can save these nodes if you wanted to, just in some stack variable. You could save them there. But it's easier to just go through and delete the nodes first. Okay? So let's delete that, then that, then that. And now, the order of the nodes also matters. Likewise, the order of the nodes, of the node deletions matters. Because, pretend, I first deleted 1. Well, I could still get to 3 through the tail pointer, but I lost access to now the 2 node. Doesn't that suck? So, how are we going to do that? Well, the idea is, in our loop, or something, when we're deleting a node, we need to save the next node so that we can use it. Okay? So idea, save the next node before we delete the current node. That way we can still reach it. So let's pretend, just in a simplified manner, I had the list 1, arrow 2. Forget about heads and tails right now. If I had some variable called n indexing to the first node, and I was about to delete the one, I would save the next node in some extra variable like that, because then when I deleted the one, I still had access to the next node. Then I could say something like n equals next and continue on my merry way. Because then n would go to this place and I didn't ever have to go through this thing that I just deleted, because it's always, remember, it's undefined to accessed memory that you already deleted. Okay, so with that, the very last thing to do, so first delete the nodes. So for node star n equals list arrowhead, n is unequal to the null pointer, n equals n arrow next. Or actually, this is a bit complicated, so I think a while loop would make things a bit easier. While n is not equal to the null pointer, because we're not going to advance always using n equals n arrow next, because we're about to delete stuff. I'm going to use a while loop instead. All right, so start at the head, save the next node before we delete the current one. Because remember, we're starting with the current one, we're about to delete it, we need to save its next node so we can still get to it. All right, so then we can do something like node star next equals n arrow next. Now we can safely delete n and still get to the next node. So you can say delete n. And now, instead of saying n equals n arrow next, because that's going through memory that we just deleted, we'll say n equals next, because we saved it. Okay? And then eventually we'll hit the end of the list when n is set to the null pointer, because that marks the end of the list. So now all the nodes have been deleted. Let's delete the linked list object. And that's the part that has the head and the tail, remember. That bit. So now I can delete the list itself, or the variable called list. And that will successfully delete everything in that linked list. Because first we deleted this one. That was like the first thing we deleted. This will be the second thing that we delete. And then this, which we call list in our function, is the very last thing that we deleted. And that was the proper order, because now we didn't have to follow pointers through something that we deleted, because that's undefined behavior. All right, so if I were to compile and run this, we should see no change, but we will have deleted this list with this function. All right, so I think that's where I want to stop today. And something that I haven't been doing in lecture is just showing you how I use Git. So at the very end, let me just clean things up a little bit. Let's remove the two compiled files, because you don't need those. And I always forget to do that anyway. So now I just have a bunch of CPP files, and if I do Git Status, it shows me that my current directory is what I haven't, is new stuff. And so if I go out one directory to the to the parent, I can say Git Status, and it'll show me that, oh, this Lec 11 folder, well, I don't know about it. Maybe you should add it. So I'll say git add Lec 11, or I can just say, just add everything that's new, add the current directory, everything there. So I can say Git Status now, and it's about to commit all of these new files, and those are exactly what I want to commit. So I'll say Git Commit And the message is added lec 11 files, let's say. And so they're all there, and so I can say git push now to give them to GitHub and eventually you as you look at these files. So that'll probably take a second, but it'll work. And I've configured it so that it doesn't ask me for my password. I've done that fancy SSH stuff. All right, so that's all I have for you today. I'll see you next time.